Hello again. Today we are going to solve a medium problem on LeetCode. This is the first medium problem in the LeetCode question series or playlist. Well, let's get right into it. Given a binary tree, determine if it's a valid binary search tree or not. Assume a binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees also must be binary search trees. So basically, what the question tells us that the keys values are unique. Less than the node's key didn't say equal than. That's something you should concentrate while reading the problem statement. And greater than the node's key didn't say or equal. So basically it's telling us, hey, all keys values are unique. So whenever a problem says a binary search tree, you must assume that it could be solved using an in-order traversal of that binary search tree. It's not, that doesn't always happens, but 90% of the time, whenever a problem statement says it's a binary search tree, then assume that it's going to be solved using an in-order traversal of that tree. Well, what's an in-order traversal? An in-order traversal is as follows. Well, here. Well, an in-order traversal is, well, basically think of it as the difference between in order, pre-order, and post-order. In refers to the place, the position that you would visit the route in. So in means between, in between. So, and you always start with left before right. So you get to the left subtree before the right subtree, the left child before the right child. So in means left, root, right. Like the post order traversal is left right root, because post means after. Pre means root left right, because pre means before. In between means in between. So why in order traversal is important to the binary search tree is because, well, it's called in order for a reason. It means in order, as in sorted. So if you have a binary tree of integers, if you do an binary search tree of integers, if you do an in order traversal of that tree, you get them in sorted order. So filling a binary search tree with some random integers is let's say 1 and 1, let's say this is 3, and this is 2, and this is 4, and this is 5. Why is it a binary search tree? Well, because every node, every left child of a node is less than the key, and every child to that child, meaning all the subtrees, is still less than that key's value, and every right child is bigger than the key value of its root. So 5 is bigger than 4, 3 is less than 4 but bigger than 2, 1 is less than 2, and so on and so forth. Of if there were more numbers. So doing an in order traversal left root right means going here, then going to the left of it, then going to the left of it, then there are no there are no more lefts. Left is null, so you visit 1. Okay, visit root, which is 2, then visit right, go to the left of it, there is no left of it, there is null left child, then visit 3, which is the root in this case, then go to the right, there is no right child, then go up here. Well, this is visited already. Well, go here, which is the root. You visited the left subtree of that node, so we visit here. Then go right of that root here. Well, here there is no left. Left is null, so you visit the root of that subtree, which is 5. Right is null. You already visited the root of that subtree, so you are done. And it's in order, so binary search tree is in order. So how to validate that it's a binary search tree? Well, easiest thing to do is check if the number, like if it was 2 1 3, then it's not a valid binary search tree, because 1 is less than 2, and in order traversal of a binary search tree must output the elements in sorted order. If it was 2 2 3, then it's also not valid, because in a binary search tree all elements are unique, and in order traversal outputs the elements in sorted order. So here it's not unique, and here they are not in sorted order. And we explained why the in order traversal outputs the elements in sorted order. So basically what we need to do is doing an in order traversal. We can do it in a recursive manner and in an iterative manner. An iterative manner requires a stack. DFS is always a stack solution, and BFS is always a queue solution. Keep that in mind also, that DFS is always a stack solution and BFS is always a queue solution. Why is it a DFS approach, depth first search? Because you go deep to left, then go up a level. Then what's a breadth first search? Breadth first search is going level by level. So you go here, then you go here, you visit all of these nodes in that level, then you visit all of these nodes in that level. But what we do here is we go deep before we visit anything. So let's start with that. What we need is a stack. Well, in Java, a stack is better implemented as a double-ended queue of tree node. Queue is stack is equal to new array dq, and we need a node cur is equal to root if current not equal to null, as dot add as the push current, and while s dot is empty, not is empty. Well, what do we need to do here? We need to so let's try to explain the iterative approach of the in-order traversal of a binary search tree. Well, to do that, we need to understand what is the difference between the iterative approach and the recursive one. In recursive, the recursive solution of a traversal in a binary search tree is fairly straightforward. What you actually need to do is implement that sentence. So you go left, you go left, you go left until there is no left. There is no more left. Then you visit that node, the last node that has no more left. Then you go to its root and do the same. Okay, go to its root and visit its root and go to its right and do the same. So basically what you're going to do is, hey, does 4 have a left child? Yup. Okay, go to 2. Does 2 have a left child? Yup. Okay, go to 1. Well, does 1 have a left child? No, it doesn't. Okay, so visit 1, then visit 2, then do the same for 3. Meaning, does 3 have a left child? No, it doesn't. Okay, so visit 3, then go to its root, then go to its root again, because you visited all of that subtree, and go to that root. Well, now you visited all of its left subtree, you visit that node and go right and do the same. So basically what you are going to do, or what you are doing, is making the base case that the node you are in is not null. When the node you are in is null, return and visit that node, then go to its right. Okay, so let's write this pseudocode. It's fairly simple. I don't know if I can type here. Let's just write it here. So private void in order r tree node n node. Well, our base case is if node is equal to null, return, else go to its left. So in order r node dot left, then visit the node, then in order r node dot right. And now we have done a in order traversal in a recursive manner. But this is not widely accepted, because if the input binary search tree is too large, it would cause a stack overflow exception, because of the stack length, of the recursive stack length, of how deep the tree is. Okay, so let's get to how to do it in a stack manner, in an iterative manner. Well, what does recursion do? Recursion acts as a stack, meaning when it finishes this, it can return to this and use that node. Like here, it comes to the null child of 1 here, it finds that it's null, then when it finds it's null, return, meaning it gets here, it visits node 1, so it backtracks to the last value. Then what does it do? It goes to the right child. Well, what is the right child? It's null, so it returns back again. Then, well, that method, that stack frame is finished and returns to the one that called it. So basically here 2, which would be at that line, so it visits 2, then goes to the right child and does all of that again. Goes to 3, well, is 3 null? Nope, it's not null. Then goes to its left child, well, its left child is null, so it returns and visits 3. Okay, it goes to the right child is null. Okay, the stack frame is finished, and 2 is visited and 3 is visited, so that stack frame, that stack frame of that subtree is finished. So it goes to 4, it visits 4, then goes to the right and visits the right child of that node, and does the same if there were more subtrees under that node. So how do we do that iteratively? Well, we would simulate the recursive approach. So we need a stack, then we go deep, we fill the stack deep from the left subtree. Well, okay, so we fill it with 4. Does it have a child? Yup. We go to 2, we use 2 as current, so current was 4 before that step. Current is 4. Okay, does 4 have a left child? Yup. So put 2, current is 2. Okay, does 2 have a left child? Yup. Put 1, sorry, not a dash, put 1, and current is 1. Okay, does 1 have a left child? Nope, it doesn't. Okay, so pop 1, visit 1, put its right child, if not null, so nothing is there, and go to its right child, so current is null. So if not null, it won't put its left child, so it pops 2, then visits 2, then puts its right child, which is 3, then we go to 3 and do the same. So eventually it would visit all of the nodes. So basically what we have to do is make a while loop here, while current is not equal to null. If current.left not equal to null, what we need to do is push the left child and change current to be equal current.left to go deep onto the subtree. When current is null, meaning that we reached the most deep left child, we would pop the stack, so current is equal to s.pop, stack.pop, and we would visit the current, and then we would push the right child onto the stack if it's not null. If current dot right not equal to null, s.push current.right, and then current is equal to current.right. So now we made an in-order traversal, but actually this is not the question. We just implemented the in-order traversal. Basically, when there is a binary search tree question, you implement the in-order traversal and you answer the question using that line, that visit line. That visit line is the solution to your binary search tree question. So basically, what we need to say, what we need to do is what we said earlier. We need to check if that number is less than or equal to the previous one. So if current dot value dot val less than or equal to prev dot val, then hey, it's not a valid binary search tree, because if it was, then it wouldn't be equal and it wouldn't be less. Current wouldn't be less than the previous. So what we need here is another tree node named prev, which is equal to null, and we would say that hey, if previous not equal to null and previous dot val is and current dot val less than or equal to previous dot val, return false, and previous is equal to current, and we would remove that. And if all of that loop is finished, meaning the stack is now empty, meaning that all of the nodes are now visited, return true, because if the stack is empty and all of the nodes are visited and this didn't get computed into a true, meaning we didn't reach that false statement, then it's not invalid, it's valid. So if we run that, it works. So let's try to submit this, but let's make sure I am in the right session. Okay, I'm not. Let's submit it, and it works. And why is it faster than only 34% of the Java Online submission? Because I'm using the iterative approach. The iterative approach is slower but more robust, more better. The recursive approach is much faster. So yeah, that's the end of the video, and our complexity is of an time complexity, because we are going through all the nodes, and the worst case, meaning that the binary search tree is valid, and our space complexity is of n, because well, yeah, it's of n, because if it was a binary search tree but not a balanced binary search tree, meaning that it's made up of all the left subtree, meaning like this. So all of it is on to the left side of the root, meaning the stack would contain all the elements, all the nodes, before actually doing something. So that's the worst case in case of the space complexity. So O of n space complexity and O of n time complexity. Thank you for the video. Thank you for continuing to the end of the video, and thank you for trying to improve yourself in the coding problems.